In this video, we will be focusing on optimizing cost. And by optimizing cost, I mean minimizing it, because we always want to pay the least amount of money. So let's get started with our first example. A farmer wants to build 2 adjacent pens, each with an area of 900 meters square. The fence around the perimeter of the 2 pens must be extra strong and costs $40 per meter. The fence separating the 2 pens only costs $20 per meter. What dimensions for the entire enclosed area minimize the cost of the fence? So I'm going to start off with a diagram, of course. So I have 2 pens side by side, okay? And I'm just going to say the widths are X and the overall length together of the 2 pens is Y. So I'll get that for my let statements. So the extra strong, expensive fence is needed on these 4 sides. So that's 2 Ys and 2 X's. And only a single X requires the cheaper $20 per meter fence. So here's what our cost equation looks like right now. Cost is equal to $40 per meter for 2 X's and 2 Ys. And then $20 per meter for X meters. So I'm going to clean this up, collect some like terms, just try to make it look a little better. And here's my cost equation. Now, unfortunately, I have 2 variables here, which isn't great. But there's a piece of information I haven't used, and that's the fact that the area of each pen is 900, meaning the overall area, so X times Y, should be 1800. And then I can divide both sides by X if I'm isolating for Y, and here we are. And if I want, I could also write this as 1800 x to the negative 1, just thinking about my derivative for the next step. And now I can go ahead and sub that in for y, and then I'll have my equation for cost in terms of the width. So I have 100x plus 80 times 1800 x to the negative 1. And now I'm going to clean this up. Okay, there's my cost equation, and now I can go and find the derivative of it. But before I do that, I am going to write my restriction. My cost equation is about x, so what is x allowed to be? Well, it has to be greater than 0, that's for sure. And looking at my length equation, it's 1800 over x. Technically, x can go to infinity, and my length will still be positive. I mean, realistically, it doesn't make sense, but mathematically, it is possible. All right, now I'm ready for my derivative. So the derivative of our cost equation will be 100 minus 144,000x to the power of negative 2. I'm going to set my derivative equal to 0 while I bring that negative exponent down into the denominator. And then I'll bring that fraction over. And now I'll just solve for x. So I'll have 100x squared equals 144,000. I'll divide both sides by 100, and I get 1,440, and then square root both sides. Now this does simplify because we can write 1,440 as 144 times 10, and the square root of 144 is 12. So there we are. But of course, the negative is not in the domain. So we're going to reject that value. And now we can go with our testing. So I'm going to test the cost at close to 0, the cost at my critical point, and because I can go to infinity, I'm also just going to double check a really large x value just to make sure that my function doesn't randomly keep dropping from that critical point. So when I plug in 0.1 into my cost equation, I get 1,440,010. If I plug in my critical point, I get approximately 7,589.47. And then if I plug in 1,000, I get 100,144. I'm trying to minimize the cost here. So this is the winner, the critical point. So x is going to be 12 root 10, and that represented my width. My length, if we look up here, is 1800 divided by x. So 1800 divided by 12 root 10. So first thing, I'm going to reduce the fraction, and I get 150 over root 10. I'll rationalize my denominator, multiply top and bottom by root 10, and then I can reduce that fraction once more. And there we go. Those are our dimensions. Therefore, the rectangle should be 12 root 10 meters by 15 root 10 meters to minimize the cost. So just to recap here, we were minimizing our cost, so we had to find a cost equation. We took into consideration which sides needed $40, which sides needed $20. Our side node equation, which also helped with our restriction, was from the area. And then we just took our derivative, got those critical points, and then did our test values. All right, next example. A company wishes to manufacture a rectangular box with a volume of 32 feet cubed that is open on top and has a square base. If it costs $8 per feet squared to produce the bottom and $10 per feet squared to produce the sides, what dimensions will yield a minimum cost? So I'm going to start with a diagram here. Here's my rectangular box. It has a square base, so I'm going to say these two sides are both x, and then I'll just say y is my height, and I'll write that. Okay, so we are trying to minimize the cost again. And we know that the top does not exist. And we know that the bottom is $8 per feet squared. The bottom has an area of x by x, so x squared. And each part of the area is $8 per feet squared. So if I have x squared feet squared, I multiply that by 8. Then the rest of the four sides will be $10. So what are my four sides? I have four sides that are all x by y. So 4xy. Clean that up. I do unfortunately have two variables like we typically do. So what information have I not used? The volume. So the volume of 32 is going to cover length, width, height. So x times x squared, times the height, y. And now I can isolate for y by dividing both sides by x squared, which I could also write as 32, x to the power of negative 2. Now I'm ready to sub that in and have an equation of cost in terms of x. And now let's clean this up. Gets very repetitive. So 8x squared, 40 times 32, 1,280. And then x times x to the negative 2 is going to be x to the negative 1. So don't forget those exponent laws. And in terms of what x is allowed to be, x just has to be greater than 0. because the height, y, will be positive regardless. There's no way to make it negative. So now time for that derivative. We have 16x minus 1,280, x to the negative 2. I'm going to set my derivative equal to 0 while I deal with that negative exponent. Turn it positive with a reciprocal and bring the fraction over to the other side and solve for x. So that will give us 16x cubed when we cross multiply equals 1,280. Now I can divide both sides by 16. I actually get 80, and this is what we're going to be cube rooting. So there's my exact value, and if I wanted a rounded value, that would be 4.3 feet. Before I solve for y, I am just going to test. So I'm going to test the cost at a number close to 0, so 0.1. And I'm plugging that into this cost equation. So when I plug it in, I get 12,808 cents, quite a large number. When I test my critical value, I get a smaller number, 445.59 approximately. And I'm also going to test a large number just to make sure that after that critical point, the function doesn't keep going down. And when I plug in 1,000, I do get a very large number. So over 8 million. So definitely here's our winner for our minimum cost. So what are the dimensions? Well, the square base is 4.3 feet by 4.3 feet. To get our height, I will do 32 divided by x squared. So 32 divided by the cube root of 80 squared, and that's approximately 1.7 feet. So therefore, the box should be 4.3 feet by 4.3 feet by 1.7 feet to minimize the cost. And there we are. 2 examples where we had to create an equation for cost, find the derivative to find that critical point that will hopefully minimize the cost.